Hello everyone. This experiment is an investigation of free and forced convection heat transfer. We have three aims here. The first is to determine the convection heat transfer coefficient. The second, to demonstrate free and forced convection heat transfer. The third is to demonstrate the use of extended surfaces to improve convection heat transfer. Actually, there are three methods of heat transfer: conduction, radiation, and convection. And this experiment investigates the heat loss of a heated surface and free and forced convection. We can use Newton's law of cooling to describe the nature of convection. In this equation, the Q is the rate of convective heat transfer, A is the area normal to the direction of heat flow, and H is called the convective heat transfer coefficient. In addition, in this equation, T surface is the surface temperature of heat exchanger, and T ambient is the ambient temperature. Actually, there are two different types of convection heat transfer. The first is so-called forced convection. It means the motion of the fluid along the heated surface is forced by devices like a fan or pump. And the second is so-called free convection. It means no additional devices are needed in order to achieve fluid flow, as the motion of the fluid it happened because of the temperature difference between the surface and the fluid. Although, from Newton's law of cooling, we can find the surface area, A, is one of the factors that determines the rate of convective heat transfer. And the heat transfer can be improved by increasing the surface area. This can be done by adding fins or pins normal to the surface to produce an extended surface. Well, this is the equipment we used in our experiment. It was mainly consisted by two parts. Well, this is the control unit. We can use the control unit to turn on or turn off our equipment by the power button. We can also use this unit to adjust the fan speed or control the heat power supplied into the heat exchanger. Although the surface temperature of the heat exchanger or the heat power supplied into the heat exchanger can be displayed on the unit. Well, this is the vertical rectangular duct. There is a fan installed on the top of the duct. It can generate an upward airflow in the duct, and the velocity of the airflow can be adjusted by the control unit. And the velocity of the airflow can also be measured by the anemometer attached to the duct. Besides, we got a thermometer here to test the ambient temperature. Well, here is our three types of heat exchangers. They are exchanger with a flat surface or with a pinned surface or with a finned surface. While in our experiment, the heat exchanger should be installed into the duct, although it was needed to connect it to the control unit. Well, this connection is a heat power supply connection. Well, this is a temperature sensor to measure the surface temperature of the heat exchanger and display the temperature on the control unit. I'm going to introduce the experimental procedure for the convective heat losses from a flat plate. First, we need to familiarize with the equipment, while the equipment was introduced just now. Well, second, we need to mount the flat plate into the duct and attach the thermistor sensor lead. Well, make sure that the plate is at ambient temperature and record the plate temperature Ts. We also need to record ambient temperature Ta. Well, next, we need to attach the cable to the heat exchanger and set the heat power to the maximum and allow the plate to heat up to around 65 degrees above ambient temperature. Then, we need to turn the power down to 20 volts. When the temperature was nearly reaching the final temperature, and we need to wait sufficient time for the plate to reach its steady state temperature. We need to record the steady state surface temperature Ts0. Well, after that, we need to set the fan speed to an air velocity of 1 meters per second in the duct. Although we need to wait sufficient time to obtain the final steady state temperature Ts1, and we also need to record the steady state temperature. Well, next I will demonstrate this experiment. Well, this is the flat plate, and first we need to attach the thermistor sensor lead. Then we need to attach the cable and mount the heat exchanger into the duct. Then we turn on the equipment and set the heat power to the maximum. Then we need to wait a short time until the heat exchanger reaches the set point. Well, when the surface temperature reaches the final temperature we want, we need to turn the power down to 20 volts. Here I just demonstrate how to operate the equipment, so the temperature here is not very accurate. Well, then we need to wait for sufficient time until we obtain the steady state temperature, and we need to record this final steady state temperature Ts0. Well, next we need to set the fan speed to an air velocity of 1 meters per second. We can check the velocity by using the anemometer and push the button on the anemometer. We can see the velocity in the duct. Then we need sufficient time to record the final steady state temperature Ts1. Now we have done the first experiment, and we need to continue with our second experiment, the convective heat losses from a pinned plate. Now mount the pinned plate into duct, attach lead and cable, and record ambient temperature. This is the pinned plate. Then allow the plate to heat to around 30 above ambient temperature. Turn the power down to 20 volts before reaching the final temperature, and again allow sufficient time for the plate to reach steady state temperature. Then we need to proceed as described in steps 5 to 7 in stage 1. And at last, we also obtained 3 temperatures the ambient temperature TA and two steady-state surface temperature Ts0 and Ts1. The last experiment is convective heat losses from a thin plate. This is the thin plate heat exchanger. We need to repeat steps 2 to 7 in stage 1 with the thin plate. Allow the plate to heat to around 21 degrees above the ambient temperature. And last, we also obtain the three temperatures, TA, which is the ambient temperature, Ts0 and Ts1, is the steady-state surface temperature of the heat exchanger. Here, I posted the results for three experiments. You can see the temperature change of free convection or forced convection for three different heat exchangers. I also obtained the steady-state temperatures for the three experiments. Well, let's check the equation. If we want to know H, Q is known as 20 watt. T surface and the T ambient have been obtained from our experiment. Now we need to know the area for these three heat exchangers. Actually, we need to measure the size of these three heat exchangers. And this is their area. After we have obtained all the parameters in the experiment, we can calculate the convection heat transfer coefficient for free convection or for forced convection. Well, now you may want to think about why the three heat exchangers have different heat transfer coefficient and what influence the heat transfer coefficient. Okay, that's all for our experiment. Thank you.